Imagine a terrifying moment when our universe, all of space, time, and everything we know, begins to fall apart. Not an abrupt end, but a process lasting billions, even trillions of years, as everything gradually gives way to eternal darkness or is torn apart into nothingness. From the brilliant Big Bang that gave birth to everything to the strange inflationary expansion that shaped the structure of the universe, and then terrifying visions of the end of space and time itself. What truly awaits us at the end of this cosmic road? Is it total collapse or an unthinkable transformation? Let's explore the ultimate fate of the universe, a journey both scientific and philosophical, challenging the limits of human imagination. We begin our journey at the very beginning with the Big Bang, an event that, according to Stephen Hawking in A Brief History of Time, was the beginning of space and time, not an explosion in space. It was the birth of space itself. After that explosive moment, the universe not only expanded, but also underwent a period of extremely rapid expansion called cosmic inflation. Inflation theory, proposed by Alan Guth in the early 1980s, solves some of the problems with the standard Big Bang model, such as the horizon problem and the flatness problem. Inflation suggests that in the first trillionth of a second, the universe expanded exponentially, becoming trillions of times larger than its original size. Inflation not only helps explain why our universe is uniform and flat on large scales, but also provides a mechanism for the formation of massive structures, such as galaxies and galaxy clusters, through amplified quantum fluctuations. These tiny quantum fluctuations in the early universe became the seeds for the formation of all subsequent material structures. Without this inflationary phase, the universe might have been too chaotic or too empty for life to arise. However, this expansion has not stopped. Billions of years after the Big Bang, the universe has continued to expand, and surprisingly, this expansion is accelerating. This was one of the most shocking discoveries of modern cosmology, announced in the late 1990s. What is driving this accelerated expansion? Scientists call it dark energy, a mysterious form of energy that makes up about 68% of the total matter-energy content of the universe, according to Stephen Hawking and Leonard Mlodinow in The Universe in a Nutshell. Unlike ordinary matter and energy, dark energy has a negative pressure, acting as a repulsive force, counteracting gravity and causing the universe to expand faster. Alongside dark energy, we also have dark matter, which makes up about 27% of the universe. Dark matter does not interact with light or other electromagnetic radiation, so we cannot see it. Its existence is inferred from its gravitational effects on ordinary matter, such as the way galaxies rotate or the way light is bent by galaxy clusters. Both dark energy and dark matter are integral parts of our current picture of the universe, but their exact nature remains one of science's greatest mysteries. The delicate balance between these components, ordinary matter, and dark energy, will determine the ultimate fate of the universe. Scientists have proposed several main scenarios for the end of the universe, each with profound implications for existence and its end. The first scenario is the Big Crunch. If the matter-energy density in the universe is high enough, gravity will overcome the expansion. The universe will stop expanding, then begin to contract. Galaxies will move closer together, temperatures will rise, and eventually all matter and energy will collapse to a single point, like a reverse Big Bang. This is a symmetrical ending and suggests the possibility of a cyclical universe, where a big crunch could be the start of a new Big Bang, creating an endless cosmic cycle, as Carl Sagan suggested in Cosmos. However, with the discovery of the accelerating expansion of the universe due to dark energy, the Big Crunch scenario seems less likely. The second, and now considered most likely scenario, is the Big Freeze, or heat death. In this scenario, the universe would continue to expand forever. As space expands, galaxies would move further and further apart, and the cosmic background radiation would cool. Stars would eventually run out of fuel and die, and black holes would evaporate via Hawking radiation, a topic we'll explore in more detail in the next video. Finally, the universe would become a cold, dark, empty place filled with scattered subatomic particles and extremely weak radiation, where there would be no more meaningful activity. Entropy would reach its maximum, and the universe would be incapable of doing anything. The third scenario, an extreme variant of the constant expansion, is the Big Rip. This scenario occurs if dark energy is not just a constant, but also increases over time, so that its repulsive force becomes so strong that it rips everything apart. First, clusters of galaxies would be torn apart, then individual galaxies, then stars and planets, and finally even atoms and subatomic particles would be ripped apart. Space and time would become meaningless, and all structure would be completely dissolved, leaving nothing. This is a truly horrifying outcome, even more extreme than the Big Freeze. Other, less widely accepted but still intriguing theories include the Big Bounce, where the universe undergoes endless cycles of expansion and contraction, or the multiverse, where our universe is just one of countless parallel universes, each with its own possible fate. In The Universe in a Nutshell, Stephen Hawking also discusses these possibilities and the profound questions they raise about the uniqueness of our universe. Current astronomical observations, especially from the WMAP and Planck probes, have provided valuable data on cosmological parameters, including the density of dark energy and matter. These data indicate that our universe is nearly flat and expanding at an accelerating rate, strongly supporting the Big Freeze scenario. The future of the universe seems to be a long and lonely journey into eternal darkness. Yet, science is constantly evolving. New discoveries about the nature of dark energy or new fundamental theories of physics could radically change what we think about the fate of the universe. We are only just beginning to unravel the universe's deepest mysteries, and each answer opens up even bigger questions. Humility in the face of the vastness and complexity of the universe is essential as we try to understand its origins and its end. Contemplating the fate of the universe is not only a scientific exercise, but also a profound philosophical experience. It reminds us of our small place in the vastness of the cosmos, but also a testament to the extraordinary capacity of the human mind to explore and explain the most grandiose phenomena. Whatever the end of the universe, our journey to understanding it is a worthy one. It compels us to keep searching, to keep asking questions, and to keep pushing the boundaries of knowledge. Whether the universe ends in a big crunch, a big freeze, or a big rip, in billions of years, each of us will be just a speck of dust in the endless stream of time. But in the present, we have the privilege of being alive, of observing, of thinking about this universe. It is an incredible privilege, a gift of existence that we should cherish. From the birth of the universe to its potential end, we've traveled a long journey of expansion and terrifying scenarios. But within those scenarios lies one of the universe's most fascinating mysteries: black holes. They're not just cosmic killers, they're also extreme physics laboratories where time and space warp beyond recognition. In the next video, we dive into inside black holes, from Hawking radiation to the possibility of black holes evaporating and disappearing from existence. Let's explore how these strange cosmic structures can emit radiation, lose mass, and ultimately disappear from existence. Don't miss it.